Good night. Now we will talk about complex networks, and we will see the structure and the representation of these networks. We will start with a brief discussion about the scope of the study between the graph theory and the complex networks theory. Graph theory uses the graph as the object of study, and complex networks focus on the problem that occurs in the network or the process that runs over the network. Graph theory is a mathematical theory, a very important theory that is the foundation of discrete mathematics, and it appeared with author about 200 or 300 years ago. A mathematician usually look for properties and try to prove theorems about the graphs. Of course, they will find theoretical and practical applications for the graphs. It's okay, it's part of their work. But graph theory studies the graphs as the object. The theory starts and finishes with graphs. We can inspect a lot of properties, we can review a lot of patterns of the graphs, but graphs are the important thing for graph theory. And complex networks is a little different because we use the graph theory very hardly. It is the most important tool for complex networks. But now we want to inspect, to study other types of problems. We want to know about real problems of your world, for instance, even for conceptual problems, not only concrete one, okay? Well, then complex networks will work with problems usually modeled by graphs. We study the problem, preparing a model of it, and this model usually is a graph or involves a graph in some way. We use other tools, for instance, statistical physics, chaos, fractals, and any mathematical or statistical tool that is suitable for the problem we want to study. We look for practical applications, for theoretical applications, for theoretical advances in the theory, of course. And most of times our interest is in large-scale problems. It is possible to study complex networks in small networks because the definition of complex networks is given by the structure of the network, not by the size. On the other hand, the size of the network is an important indicator because some tools are not efficient for different size. Okay, we can say that complex networks focus on the studied problem or in the meaning of the graph and its properties. Okay, we will inspect the graphs, we will discover properties and patterns, but not to study the graph, but to study the problem that involves the graph. Okay, we will advance a little more than graph theory in this sense. I present to you a graph. In this picture you can see 3 regions according to the size of the network. For small networks, we can inspect individual nodes if we want. But on the other hand, it is very difficult to use a statistical tool. Imagine a network with 10 or 12 nodes, and you are trying to give a frequency distribution. Difficult with very low, very limited use. But it is possible to know each of the node. It is possible to know a lot of its network, and maybe the problem that involves the network is very interesting. In the other extreme, for very large networks, it is infeasible to inspect each node individually. Then we need to use the statistical tools, because we will not even see the network as a whole. Trying to draw this network in a paper or a computer screen is a difficult task, and most of the time it's not possible. You will finish with a draw, okay, but it is difficult to draw conclusions of the picture. And we have an intermediary region that is suitable for the two types of the studies. Tools for small and tools for large-scale regions. In this course, we will talk about medium-sized and large-scale networks. We will not focus on the small ones, okay? And we will work with representations of the network, because, for instance, it is impossible to bring to our classroom a complete national power grid. Then we need to represent this network, this problem, for instance, in some way that we can do it. But we will pass for very basic concepts again, only to remember. A network is a collection of nodes and edges. Nodes are the elements of the problem. They may be cities, they may be electrical substations, computers, voters, people, everything. And edges represent relationship among the elements, specifically between two elements. Okay, there are sophisticated types of edges, but we will talk about simple edges. A simple edge expresses a relationship between two elements. If this relationship has a preferential direction, then we will call the edge arc. Arc is a relationship that is directed from one element to another, okay? Then the very basic elements of any network are the nodes, also called the vertices, and the edges. Sometimes the edges are arcs because of the preferential direction. Of course, we can use additional pieces of information to represent a network, and most of times we do it, okay? And we represent the networks in several ways according to our interests, according to our objectives. Most of the times we want to bring some representation of the network to a computer because we have tools to analyze, to work with the network. Then I will talk to you about some of these representations, okay? Starting with operating representations of networks. And the first representation comes from graph theory. We use adjacency or incidence matrix. An adjacency matrix indicates the relationship between a pair of nodes with a value of 1 in the intersection of the line and the column of the matrix. Then, if I have 1 in the position according to the line 2 and column 3, I know that there is a relationship between this element 2 and the element 3. If there is a 0 in the position, I have no relationship between them. Okay? An incidence matrix do the same, but the focus is on the edge, not on the node itself. Adjacency and incidence matrices are very good to operate representations of complex networks. They have a very strong mathematical focus. They are easy to do calculations, and for computer programs they are very interesting. But they have some drawbacks, because for sparse matrix or graphs and networks that are not so dense, we will have a lot of zeros in the memory. Then we will waste memory and time processing trying to sum, to average very long series of zeros. Then adjacency matrices are good, but they have this limitation for large networks that are sparse. Okay? If you prefer, you can use adjacency lists. Adjacency lists do the same as adjacency matrix, for instance, but we use linked lists, another data structure in memory, and this data structure is very good if we have sparse matrix, or in our case sparse graphs, because only the values in our interest, the pairs related of nodes are represented. Okay, then we don't waste space with zeros, with indications of absence of the relationship. In this sense, adjacency lists are very efficient. Of course, they have some drawbacks, because if your network is very dense, you have almost all of the possible relationships, you will waste more space, because you need the space for the indication of the relationship and for the management of the list itself. Okay, and the algorithms process adjacency lists are more sophisticated, more complicated than algorithms for matrix. Okay, adjacency list has a computational focus. Okay, because we wanted to reduce the amount of memory and sometimes the processing. We do a very good memory optimization if the network is sparse, and we have a very easy way to improve the navigation speed, because in adjacency lists we can use uh, memory pointers, and they are very fast in moving from one point to other. It is easy and fast to find another element in the network, but the algorithms are not so simple, okay? We have talked about two operating representation, adjacency matrix and adjacency list. And you can see that both can represent the same network. You will find a better choice according to your problem. Okay? We will see other types of representations. Graphics, figures, drawings are very good representation of graphs and of networks. We see in the slide several possibilities, and we can see that the figures have a very important way, because we can get insights from the network, looking the picture. Then we can see in this slide bipartite networks, different densities of network, different arrangements of the elements. The charts, the figures they have focus on visual analysis. They are good to help the understanding of the structure of the network. We can get insights from the network, and sometimes we can insert artistic elements in our study, usually to highlight some details of the network, to show patterns of the network, and so on. We can use properties vectors to represent networks. Usually, we will not have an exact map of the network. We choose a list of properties and we build a vector of them, of course with their values, and we can operate it as linear algebra. Okay, a very powerful representation, a very compact representation, because, for instance, a very huge network may be represented by 5, 10 integer values, for instance. Then we have a very compact network, but we have no exact map of the network. Okay, we can reproduce networks that have the same properties, but they are not exactly the same. They are very similar. They have, from the mathematical point of view, the same properties, but not the same chart in a very precise sense. Now, properties vectors are good representation of network features. They are very good for comparisons, because sometimes we don't need precise details of the networks. We need to study the properties of them and properties vectors allow us to do fast and good comparisons. We can use it to do ratings to classify the networks in some way, and we can use the property vectors to reproduce the network as I have said. A very important tool for large-scale complex networks are statistical distributions. We can see in the figure some of the charts of the node degree distribution. It's a very important measure for complex networks because the distributions gave us a lot of information about the network, about the structure of the network, and sometimes about the origin of the network, the process that model that network. Then, statistical distributions are very, very important too, and side by side with graph theory will be used in almost all the research works in this field. Statistical distribution help us in the identification of the network, in the knowledge of the structure and its invariants. It's a very strong point because sometimes we see different networks, but for some measures they are invariant, they are the same. Okay? And statistical distributions help us to locate these invariants. Again, we can use it to do ratings, to do comparisons, and is the tool of choice for the treatment of large networks. Well, we have another type of representation. This representation is the model. We have a lot of type of models: mathematical models, statistical models, computational models, physical models, and so on. Usually, the model is used to define a family of networks. Then we prepare a model, and this model will instruct us as a cake recipe to prepare a network. Okay? This model can evolve from any area, but at the end the model specifies how I will reproduce or recreate or generate a realization of a network. Models are a representation of the reality, but always a simplified one. Okay? Each time I use a model, I'm losing some details of the reality. For all representations we had seen until now, it's true as well. When we represent networks in a computer, we abandon some details. Models are good representations because we can sophisticate this model as much as we desire. Okay? If we want to work with a simple model, it's okay. If you want to produce a very sophisticated model, it's okay as well. But it depends on the problem, it depends on the study we want to do, and sometimes it depends on the data that are available about the network. It's useless a very sophisticated model without data for support. Okay? And we get a model and we generate several copies. We call it realizations of networks. It is important to perceive that we don't do a lot of copies of the same network from a model. We do a lot of realizations, a lot of individual new networks according to that model, and you use this set of networks, for instance, to do simulations, to look for patterns, and so on. The models are very, very interesting and a very useful way to work with complex networks. There are two types of models, basically: static models and dynamic models. We'll talk about them because you need to understand the difference between them. Static models usually define the final state of the network. Your network has a certain number of nodes and a certain number of edges, and the edges are connected to the nodes in this way. It is a typical static model. Dynamic models indicate how the network will evolve. Then, usually they are in the form. You start with a set of nodes in this way. You add or you remove nodes and edges in a way or another way. Okay? Then you don't specify the final state of the network. You will do the process of evolving or growing the network until you want. When the network reaches a state, a size, an order that is suitable for your purpose, you stop the growing of the network and you have your network to work with. But models are not restricted only to the structure of the network. We can use models about the process over networks. Sometimes we call operating models or process dynamics. They are models that try to capture, to understand the process. For instance, we can model the structure of a social online network. It's a topological model, usually a dynamic model. But how about the communication among people in the network? This communication, the message exchange among the people, is a process over the network. This process only occurs because of the network. Then we can use models to this type of process. How I can simulate or reproduce or understand the message exchange among users. How I can understand the streams of energy in a power grid, and so on. Models can be as sophisticated as you imagine, or your computer allows, okay? Then we can put a lot of additional data in a model, a lot of calculations. We are not restricted only to matrices and lists processing. We can use them, we can use the statistical distributions, we can do a lot of things to improve the quality of your model. And usually we support the model processing with very sophisticated algorithms coded in programs, efficient programs, because we wanted to have a fast processing as well. These models can use additional data, specific features of some class of problems, for instance. Then I like very much. I work with the models of complex networks, and I think they are very good to work with. Okay. Then we talked about the structure and the representation of complex networks. Only to remember, we started with the difference between the focus of graph theory and the complex networks. Graph theory studies the graph as the object of interest. Complex networks study real problems, large problems, as the object of interest. That we needed to bring some representation of the network to our environment, to our research or study environment, because the network itself is impossible to claim. For instance, how I can bring our people in a social online social network to the classroom. It's impossible. Then we started with the basic elements to compose the structure. We talked about the nodes, the elements of the problem. We talked about the edges, that are the relationship between the elements. And we saw that sometimes we use arcs to differentiate direct the relationships. Then, with these very basic elements, we saw a lot of operating representations. We can use adjacency matrix, incidence matrix, adjacency or incidence lists as well. We can use drawing features, photos, it's possible. We can use statistical distributions, and we can use models to work with the networks. Now you know a lot of tools to bring your real problem to your research environment, most of the times to your computer. With this set of tools, you can analyze the network. We can draw conclusions about your problem. Thank you for your attention. Until the next class.